All right, hello everyone. Checking delay. I think the camera's fine. I'm Professor Caudill. Hope everyone's doing all right. So today we're gonna start on number 80. Number 80. Okay, so velocity particle moving along x-axis. Particles moving this way. Let me see if I can adjust the size of the brush. Decrease brush size. Decrease brush size. Okay, there we go. Okay, so VT is A plus, I think we've already done this one. Have we already done this one? Yes, we've already done this one. So scratch that. 81, we've done that. 82, we've done that. 83, 84. Okay, let's start at 86. Okay, so 86. Particle moves along x-axis according to, I prefer S of t. Originally, when I actually took a calculus course, I thought this was the worst thing. Kind of more sympathetic to it now. So what are the velocity and acceleration? Okay, so we're going to take negative 4t, and then this would be negative 4. Okay, so it looks like it's constantly accelerating. So at all points in time, it is decelerating 4 meters per second. Okay, so we're just gonna do S. So if you don't know, I'm using Newton's notation. S dot. It's basically saying ds dt, which is basically saying ds t over dt. It's just compact notation. So we're doing s at t is 2 and 5. Okay, so that's going to be negative 4 times 2, negative 8 per second, and negative 4 times 5, negative 20 per second. Pretty easy. Let's move on. Particle moves at a constant acceleration. Okay, so A is, let's say, a constant. V okay, so V at 2 is 2t. No, it shouldn't be that. V at t is 2. V of 2 is 2. Okay, V 1.52 is negative 7.6. Okay, so we want to find the constant acceleration. So I think we're going to use this equation, v minus v naught, t minus t naught. So acceleration should be 7.6 minus 2, or 1.52 minus 2. And I think I had the calculator I added last time. Okay, so we should be able to use equation 0. So we're going to use equation 0, final velocity, negative 7.6. Acceleration is what we're solving for. Final time is 1.52. Initial time is 2. Initial velocity is negative 2. So we're getting 11.7 meter per second squared. Okay. Moving on. 88. Train is moving up a steep grade. So velocity is constant. So that means acceleration is 0. Now how do I know that? The integral of Vt is saying the integral of k dt is the integral, no, I'm sorry, we're d dt of v is 0, because d dt of a constant k, it's really saying constant k times t to 0. So that would be negative 0, negative 1. So it would be k t actually. So let me just verify. So say x is a symbol. No. Q, let's say symbol Q. So if symbol is a constant, differentiating Q is 1. Don't think that's correct. K and 0. Show steps. The derivative of a constant is 0. Okay, so just ignore that. I know the derivative of a constant is 0. Prove that the derivative of a constant is 0. F of x equals c. So you take the limits. C minus c, 0 h, 0. Okay, there you go. I showed you the proof. It's good enough for me. Hopefully it's good enough for you. Okay, so we know it's velocity. Something breaks loose, starts rolling freely. Okay, so seems to just be similar to the free fall problems. So I could just rewrite this as some mountain and a rock falls down. V naught is K. After 5 seconds. Okay, so after 5 seconds, Carlos, the rock is 30 meters behind the train. So let's say V naught, say Y naught 0. So Y final is -30. We'll probably use gravity in this scenario. And we'll use positive gravity since we're going below the y-axis. Hope that's correct. Double check yourself that this is true. When we're, going below the x-axis. Okay, so y is -30. We want to know the acceleration of the carbons. Okay, so we can't just say it's gravity. Okay. So this is anything makes this calculator very powerful, it's going to be what we're about to do here. So we're going to do equation 5. Final velocity is V A displacement -30 0 initial velocity V naught. Okay. So A is -k squared over 60 plus k squared over 60, which is 60 over plot k squared okay, so that's our acceleration, is whatever k's velocity. So what about the time? I feel like we should be using the time. Okay. So what if we plugged it in here? Equation 0, final velocity is v, acceleration, final time is 5, 0, initial velocity okay. We are also getting a okay, we're also getting a constant acceleration. So I know gravity has to play a role in this, but I don't know how to. It should just automatically be calculated. Okay, so what equation are they using? 1/2 V naught. So you're using this. Okay, so let's see if we can get what they got. So let's try east, end at 30. Oh, my bad. 0, end at 30. Oh. Okay, I want to do equation 4. Okay, equation 4, -30. Acceleration 5, initial velocity is 1. Okay, so I just calculated 2.8 meters per second squared. I plugged in constant velocity as 1. They are getting 2.4, so we're off by about 0.4. Pretty close, I would say. -60 divided by 25. -2.4. Okay, so that's kind of bothering me. Why? Is our calculator off? V naught. So they have V naught for 0. V naught for 0. But that's not right, is it? Initial velocity is not 0. The question specifies it's constant. So I'm gonna say acceleration is 2.8 v, or -2.8 k, whatever that constant is. All right, so let's move on. Second part. Oh, no, there's not. Okay, let's move on. 89. Electron is moving in a straight line with a velocity of 4 times 10 to the 5. Enter the region 6 centimeters long. Okay, so let's say x naught is here, and this will be x. And it accelerates at x naught. Okay. What is the velocity? Okay, so this is going to be v naught here. And we want to find the final velocity. Okay, so shouldn't be too bad. And then we're going to take all that And we're going to find key. Okay. Shouldn't be too bad. So we're going to use equation 5. So final velocity is what we're solving for. Acceleration is 6 times 10 to the 12. Displacement is x. Do we know x? Okay, x is 0. Okay. Okay. 5, 0. Initial velocity is 4 times 10, 5. Okay. I'm gonna choose the positive answer in this scenario because the velocity, initial velocity and the acceleration are they're both positive numbers. So we're getting some number 8 times 10, 3, 4, 5 times the square root of 94. $9.7. Okay, so it's approximately 8 times 10 to the 6. Or 10 to the 7 seconds. That's false. We solved for B. So V is approximately 10 to the 7 meters per second. Okay, so now we want to find. Okay, now we're going to plug that into another equation. So we want to find T given all right, so V naught at probably can do equation 3. Okay, so the final velocity is 10 to the 7 approximately. Acceleration 6 times 10, 12. T is what we're solving for, initial velocity 10, 5. T in this region is 1 out of 62. Okay, we're going to say 1 times 10. No, we'll say 6.25 times 10 to the negative 345 seconds. Okay, and this is an odd problem, so we can't check our answer. 89. So they're getting 8 times 10 to the negative 8. Okay, we're kind of off quite a bit. I think we're close. We did round v, so whenever you round something, if you calculate it again, it's going to be even off more. I remember our last answer was thinking maybe we messed up the scientific notation. Let's try equating 5 again. So we had final velocity was what we solved for. Okay, so now we're getting a different number, 200,000. Five times 10 to the 12. Oh, that makes sense. 5, final velocity, v, 6 times 10 to the 12. 5, 0, 4 times 10 to the 5. V is equal to 8 times 10 to the 5. Okay. So the book is getting this number. I mean, okay, we can just calculate it. Yes. 3. Okay, so when I actually calculate it, I get 10, I get 8 times 10 to the 6. Eight times 10 to the 6. Book's getting 8 times 10 to the 5. So not sure. Maybe we should double check this is correct. Two A. Okay. So I'm guessing the book's wrong. Where I'm bleeding at. Let me verify everything's right in our code. V A X seems to be right. V A X X naught B naught. All right, so yeah, I'm gonna say the book got that one wrong. Okay, let's move on to number 90. Ambulance rushing a patient to hospital. So V naught 72. She must travel. X is 50. X naught is 0. T is 2. A is that, and then okay, so 90, probably equation 4. So 50 meters, acceleration is what we're solving for. Time, 2 seconds. I should check the units before I accept this answer. 72, initial position, 0. So we're getting negative 47 meters per second squared. So, the ambulance. Does that make sense? I don't. Ambulance should be accelerating positively, right? All right, so I mean, I guess the ambulance could slow down and still make it. So I think our answer is reasonable. The minimum is negative 47. If she goes negative 48 meters per second, it's gonna hit a red light. Um, what's the speed? Okay, so speed is, we're going to take, what is that, equation 3? Speed is, solving for v, negative 47. Time is 2, initial velocity, 72. Okay, so I think in 22 meters per second. Okay, so I'm about 50-50 on that one, that I got it right. Motorcycle is slowing down uniformly. Motorcycle is slowing down uniformly. Is that constant? Like, I guess uniformly is a constant deceleration. So let's just say A is a constant. It's a negative constant. Covers 2.0. Okay, so X is 2. Oh, I did want to check my units. Okay, so this is 72 meters per hour. 72 meters per an hour. To convert this to seconds, I think we take times minutes in a second. So this should be 72 divided by 3,600 meters a second. Okay, so that might change our answer. So final velocity is 72 over 3,600. Acceleration is what we were solving for. Displacement is 50. Initial position is 0. Initial velocity 72. We want to use equation 4. So this equation 4 displacement is 50. Acceleration is a t. No. Okay. Try again. Equation 4. 50. Solving for a. I don't think this acceleration is right. T is 2. Initial velocity is 72. Initial position is 0. Oh, I didn't change it. I'm really struggling with this one. Acceleration is a. T is 2. Initial velocity is 72 divided by 3600. Initial position is 0. Okay. So I'm getting 25 meters per second squared. Okay. I think we plugged in this into equation 3. So final velocity we're solving for 25, 2 seconds, 72, 3600. Okay. 25. Okay, so I'm getting 50 meters per second is when crosses. So she has to, if she accelerates any slower than 25 meters per second, she hits a red light. When she crosses a red light, at the minimum, she'd be going 50 meters per second. Okay. Good thing, so this is why it's important to check your units, because yeah, you want everything to be consistent. So where are we now? 91. Okay. So T final is 120. T0 is 80. Okay. So we don't find A. Two kilometers in 80 seconds. Okay. This might be a tricky one. So we don't have any velocity. No velocity. So that's kind of a problem. So we should probably start by finding a velocity, right? Probably use equation 2. Equation 2, displacement, 2 kilometers. Time. Oh, do I do average time? Do I do Do I do 100 seconds? Initial position 0. Okay. 0.02. What's our units? Kilometers a second. Okay, this is an odd problem, so we can't check our answer. So now we're gonna find the acceleration. So let's try. Let's try equation 4. 2 kilometers. Time is 100 seconds on average. 0.02 kilometers per second. Initial position is 0. Acceleration is 0. Okay. So I feel pretty lost. So we're gonna look at this. 1 kilometer. Okay, so our V naught is close. V naught is close. Then they convert this into hours. Convert this into 50. Okay. I don't know what they mean by solve simultaneously. I'm guessing like they're isolating V naught and then they're plugging that into here and they're plugging that here to get these numbers. Okay. I want to move on. It's 92. Cyclist travels from A to B in 10 minutes. So T is 10. X is B. X naught is A. First 2 minutes, so zero. So let's just say T. So 0 to 2 minutes. A is 0.09. Okay. She then travels at a constant velocity. Okay, so does that mean 7 minutes? Constant velocity. So V is a constant. Next, she accelerates opposite to the motion. 3 minutes later. A is some negative. Let's just say C. What's her acceleration during the last 3 minutes? Okay. Acceleration during the last 3 minutes. What is the acceleration during the last 3 minutes? Okay, so we have to be careful here. Okay, let's just send equation 1. Final velocity -1, -1, 10, 3, no. So solving for A, so 0, 1, A, 10, 7, velocity. Let's get a second opinion. Okay, so it's saying this is point 18 using V equals A. No. Initial velocity. So it doesn't even calculate to V initial. We just assume it's 0. I'm assuming V naught is 0. Okay. So this is going to be V is A 2 minus 0. So it's going to be V is 0.18. Okay. Yeah, I don't really believe the Ling model here. We'll just move on. Okay, two trains moving at 30 meters per second in opposite directions. This one's going negative 30. The other one's going 30. On the same track. That's not good. So one is going 30. One is going negative 30. Okay, so 30 meters apart, so 0. So x is 0. X is 1,000. Okay, assuming both brakes have the same acceleration. Okay, so T accelerations are A. A of T1 equals A of T2, train 2. What must this acceleration be if the trains are to stop short of colliding? Okay, so we need to stop here. We need to decelerate to be here. So really, we want to find x, let's just say x star is 500 meters. Okay, so we want to find A. We don't have a time, so we're probably going to use equation 5. So the final velocity is 0. We want them to be stopped. Acceleration is what we're calculating. Displacement is 500. Initial position is 0. Initial velocity is 30. So we need them to decelerate 0.9 meters per second squared. Let me check the units. Okay, so let's check. And the book gets the right. Book gets this answer as well. So, of the whole video, this is probably our best work solving this one. So you don't really, yeah, I mean, you do need to know the other train, but okay, great. Awesome. Let's see if we can knock out another one or two before we run out of time. Okay, 10-meter truck is moving with a constant velocity of 9.7, so and x equals 10, and this is moving at 97 kilometers an hour. Okay, so we have to watch our units. Okay, and it passes a x not equals 0. It passes a 3-meter car. This car is moving at 80 kilometers an hour. So we want to find T. We want to find T when the front of the truck is on the X0. Okay, so first we need to convert the lengths to kilometers. So that's take 10 meters times how many meters are in a kilometer. It's about 1,000 meters. So X is, so the 0 is going to cancel out. We're going to get 10 to the -2 kilometers. Okay, likewise, this will be 3 kilometers. Okay. So now we can plug things in. So we're trying to find it's going that fast, this is going this fast. We want to know when solving for T. Probably going to use equation 4. Displacement. So guessing it'd be 10 to the -2 minus 3 1,000ths. Okay. Acceleration. I don't know acceleration. So don't know time. Initial velocity. I know it's gonna have to, we're gonna do some like equation. Let's say we're gonna do some equation and then we're gonna plug it in to another equation. So maybe I can just have it, don't solve, just reword. Question asks for the time it takes for the front of the truck to align with the back of the car, and then for the back of the truck to align with the front of the car. So we know x naught globally is 0. So this whole line is going to move to here. So I guess we could just say It's just like it's just very complex. It's just a very complex question. So let's see how the book does it. So they just converted the 97 into meters per second. We could have done the opposite. So I guess the key is relative velocity. So I haven't seen that term before. I don't even think the book in this chapter covered relative velocity. So velocity relative equals velocity of the truck minus the velocity of the car. And then you take first alignment, take t, it's going to be 10 minus 3 over VR, I'm guessing. So, oh, I guess they're adding it. Total distance. Okay, well, I get kind of annoyed when the book just pulls things out of the hat. Like sometimes it'll assume you had to look up the velocity of this or the speed of sound, even though it doesn't give you what that is. It just kind of assumes you're supposed to pull it out of a hat somewhere. Same with this problem. It's just kind of assuming you know how to calculate relative velocity. But maybe there's another way that I missed. But yeah, thanks for watching. We'll pick up on 95. Police car. All right, see ya.